Yeah, thank you for the opportunity to present at this, and I've really been impressed with all of the presentations and the ideas that they brought forth, and I found myself nodding my head so many times, like, "Yep, yep, I really get that. I understand what you're saying," or once in a while, it's like, "Oh, I hadn't considered that." So I guess I feel like I'm kind of the final act, following a lot of very excellent acts. So I hope you'll bear with me as I go through this because. The interesting situation that we're involved with at EarthScope is that we are a merger of two prior organizations that ran major facilities, one for seismology, so that's dealing with earthquake data. And the other one is dealing with geodetics, so dealing with GPS data, ground position, slow slides and so forth. And so it's really difficult right now to talk about our our current state of the situation in terms of data ingress in a concrete way, because as it happens, we're still building out a new system. We have this unique opportunity to come together, figure out how each other has, the way they've conducted business and actually compare and contrast and then rethink how we're going to um, function as a more unified organization. But I will start off with kind of a retrospective on the seismic and geodetic sides in terms of we've been around for 30 plus years as functional data repositories. And on the geodetic side, most especially, they are uh, basically first-class network operators operating a vast majority of the GPS instruments that come into that center. Whereas on the seismic side, where I came from, which is IRIS, we operated instrumentation in the field globally to a small extent, but a bulk of what we store comes from a lot of other network operators, a lot of other institutions, a lot of other scientists. So when you look at the growth, even just from 2004, these plots just represent a single decade. You can see how the amount of data that we've accumulated has climbed beyond just a linear line. And if you extended this back to like 1994, it basically looked like a flat line at this scale. We would have to change it to a logarithmic presentation to be able to see that change. So our technologies have had to keep pace over time since the 1990s, where we were storing basically in hundreds of gigabytes. I remember when I first started there, we had a 6 terabyte automated tape storage system for the mass store. And so we've gone so much further since then into RAID systems that have increasingly scaled into the hundreds of terabytes, and now we find ourselves at petascale in terms of what we're having to wrangle. So our combined storage at this point is about 2 petabytes worth of data. And we expect that that is going to continue to grow because, like with so many sciences that we're seeing, like the Vera C. Rubin Laboratory and CERN and so forth, is we're getting really good at capturing huge amounts of data very quickly. And the barrier to entry to getting instrumentation placed in the ground for seismic or geodetic purposes is becoming increasingly cheaper. We're able to invent ways to increase our sensing capacity orders of magnitude. So all those factors mean that we expect that the storage curve is going to go way up in coming years. So with EarthScope, we are presented with a variety of sensors that we are either involved with the data itself, or we are also involved with the instrumentation and the gathering of that data. This goes all the way from polar instruments for folks in Antarctica. In fact, I've been seeing regular pictures from our colleagues in McMurdo. They've been repairing a lot of GPS stations there, and we've gotten a lot of those back up to 100% capacity. But we have the standard seismometers and GNSS instruments that are both very dense in the North Americas as well as around the globe. Borehole strain meters, which we have at certain observatories. Magnetotellurics is still something that we are getting more and more involved in. We consider that the data management for MT to be still kind of in its nascent stage. And then we have imaging sources that we make use of from unmanned aerial systems and most importantly SAR. We are part of the Open Topography program, and we work very closely with that. So lots of different sources we work with and a lot of different scientific instruments. And we think that bringing a seismic facility and a geodetic facility offers incredible opportunities for data fusion and making new cross-disciplinary discoveries. Backing all of this backing all of this work in terms of gathering data are a variety of networks that we support and draw data from. On the geodetic side, as I mentioned, our facility manages a lot of the bulk of the instrumentation. It's more than 1,000 stations related to NODA, which is North Network of the Americas. But we also have partnerships for other forms of data collection. And so this amounts to about 85 permanent networks. Standard sample interval for these is about 15 seconds and then 1 hertz for high rate. So we can actually go and re-request high rate data when we trigger on a particular event of interest. And that may sound like a slow sample rate, but it's actually extremely dense data because with geodetics, you are bringing back information from beams that come from multiple satellites that are flying over all the time, and any given receiver generally will get reliable data when they have 3 to 4 satellites that can actually look at that can be seen by that receiver. For the seismic side, we've been uh, caretakers of data from 174 real-time networks, and historically we're actually in the thousand, well, not the thousands, but there's in our metadata database there's something like 1,100 total networks that we can actually reference historically. So the typical sample rate for seismic data these days is about 80 hertz. That's kind of our typical broadband. It's become a more common to see 100 hertz. And then we get channels that vary from zero point 0.1 hertz to as high as 500 hertz. To some extent, we can get even higher rate data, but that's not as common. So Global Seismic Network is something that EarthScope manages. Our biggest partnership internationally is the FDSN, and this is our kind of our doorway to cooperating with institutions around the world, capturing and providing open access to their data sets, as well as what's important is we have an instrumentation center in New Mexico, and we provide portable seismic instrumentation to PIs to conduct experiments. And those tend to be either passive arrays or active seismic arrays. There's a variety of data feeds coming in related to each discipline. For seismic, we're doing a really good job of kind of regularizing the community around one form of data feed. So we have this SeedLink protocol that is internationally recognized, and this transmits mini-seed data. So I think the seismic community has done really well in rallying around standards that keep down the variability of what we have to deal with. On the geodetic side, there's a system that they maintain they call Jupiter, and this is a uh, very good management system for getting TCP delivered real-time GNSS. And then there's some other these GPS flow, BSM flow, tilt flow. This is more for batch access to remote stations. So there are some stations that only collect data internally to themselves, and these systems then do polling, generally on the hour, and collect data in batches. So I'm going to be describing our general model for data collection for archival, and not getting too specific into the names of any systems, some of which are actually homegrown. We have a lot of things that are ad hoc because they've been historically the best solution for what we needed at the time. But what's common amongst our data collection systems is we have some kind of real-time data feed manager that seeks that has uh, a catalog of configurations to reach out to remote sites that actually do the initial collection from stations. So as I mentioned, um, uh, we're either on geodetic side, we are actually talking directly to receivers and accessing the data from them using VPN connections. Or on the seismic side, we tend to go to a secondary data collection site where they stand up um, a server that we can then contact and maintain a connection to get real-time feeds. So it generally follows this model in one form or another, bringing in multiple streams. For seismic, I know that we have like about 4,000 stream. Well, let's see. It's not 4,000 streams. That tends to be what's going out. I think it's more like hundreds of streams coming in that can have a number of different channels from a number of different stations. But it amounts to a lot of data coming in. And the first thing that these brokers do is they put it into some sort of collection buffer. Historically, what we've used on the seismic side is a ring buffer, and our preferred technology for a couple of decades has been Antelope for acting as this ring buffer type of situation. But we are starting to remodel how we're actually doing that collection. But in any case, when you first reach that collection point, you have to make a decision about whether this is the format that you want to actually have propagate into a settling database or a settling pond. If not, if it needs to be normalized to a particular standard format, then you can run it through a converter. And this is where you'll sometimes see these workflows that have very specific vendor um, uh, conversion solutions, like, RevTech to mini-seed, that kind of thing. So this conversion takes place. And then we decide whether there needs to be any additional tagging or enriching of the metadata that's attached to this record that's coming in. And this is where messaging systems start to make sense, is because then you can actually convert that data record into a richer representation as a message. But in any case, you can, once you have this necessary information, you put it quickly into a settling DB. And this is kind of the first resting point for data to come in. Anything that's time oriented, you have to account for the fact that you might get data that's out of time order, that as it comes in, it might be out of channel order. You may get some gaps that you need to go back and refill. A settling database is a really great place to collect and assess about whether you actually have a complete data set that is ready to be staged for archival. There's a metadata database of one form or another that supplies any additional information that you may want to include with that data record. It can be useful for adding that information. So the metadata is our place where we're keeping track of what we have out there in the world that's feeding us data. And it goes from anything dealing with how we identify it to all the way down to what are the response characteristics of the circuitry within that system that results in how the digital time series is measured. So for the curation to archive, this is a point where the settling database has been collecting data for some time, and some of your data sets are now basically kind of in a quiescent state, and there becomes a point where it's actually appropriate to now start moving it to the archiving system. So for the settling database, you want it to be something that's highly transactional and quick to mutate and modify, whereas you don't necessarily want to do that with an archival storage system where you're constantly doing upserts and updates. So the settling database acts as a nice transactional location to get things to settle out. A timer kicks in that makes an assessment of kind of like what time span or what extent of data sets in that settling database are ready to be extracted by some kind of spooler into the archival storage. And so at that point, we have the opportunity to do a few additional steps to prepare it on its way to becoming archive ready. We interact with a metadata system again to see whether there's anything in this data stream that has new metadata that we need to update in the system. We can update the metadata system, but then we also can further enrich and tag the incoming data from what we have in our metadata system, providing those additional details. At that point, with the archival system, um, initially what you end up doing is you're just inserting data into that storage system. But because the archival system is something we curate and we maintain and we modify and so forth, we have to start thinking in terms of upserts and upversioning of data. And so at that point, we ask the archival system, it's like, do you have an existing version of this data set, maybe from a prior timestamp or something that we want to pull out, add these new elements that we're bringing in, repack it, and put it back in the archival system. And so you can either go as simple as a full overwrite of what is there, or you can go so far as to have a versioned update. In order to facilitate later retrieval of the data from the storage system, you want to have some sort of catalog that will keep track of where you can actually go back and find a particular data set. And so that catalog serves as a lookup for anything else that wants to do a data extraction later. And finally, you might want to actually do some sort of status update as far as the state of archive completeness or the latest date archived or so forth, and plug that back in the metadata system as well. Um, the findability triangle is something I kind of it sort of popped into my head, and I don't know if I don't think it's a standard term, but it's something that we think about in general terms when we're thinking about not only how we store this data, but what is going to be the access pattern for most individuals, most researchers, when they're trying to find data in a 2 petabyte or multiple petabyte data system. So first, you want to have a fast transactional system that allows you to do filtering, to ask, what do you have? A lot of times people are just wondering what's there. And that this could be time bounded, it could be geographically bounded, it could be based on instrument type. So that first question is generally provided by a metadata system, which can provide a pretty lightweight response in terms of what you can expect to be able to ask for. The next is to ask whether it's available, maybe again, for those certain parameters you're looking for. And if so, where is that? We could have a complex form of storage, maybe multiple archives, maybe things are distributed in various locations. So the location catalog acts as your lookup for finding what is available and basically providing that initial roadmap on where to look for it. And so hopefully what comes out of the process of locating it in the catalog is a technique that makes it easy to access. And so this is where either a very well-defined URL pattern is good, or in many cases, it's actually better to have some kind of web service-oriented broker that acts on your behalf to go take care of the extraction. So that having the knowledge of how to access it is something that comes out of those previous steps. And finally, once you have the data, many times there are a lot of details that you need to provide that go along with the data that describes that instrumentation in detail. so that you can actually conduct the science. And so you'll be brought back to talking to the metadata system to do more drill down on, the data about the data. Um, Microservices and web services has become very prominent within EarthScope, the EarthScope facilities in the past 10 years. So this has really enabled us to increase our capacity to scale out both data exchange and programmatic workflows. It's been a huge enabler for so many researchers and also for us building complex systems within the data repository. So we've typically gone with HTTP-based REST APIs because they're just very accessible and flexible and very easy for public users to make use of. Uh, REST services are stateless, and so that encourages the development of highly decoupled data exchange between systems. And so this is a very important property that leads to good scalable design. Horizontal scalability is easy to attain through the use of load balancers, and you can spread connections over multiple servers. And finally, a good microservice architecture then lends itself easily to migration from on-prem servers to the cloud, because the cloud is a place where we have to think even more abstractly. So I'm just showing you a kind of a depiction of what our GNSS real-time system is. So this is just a slice of what we have built out in our systems in the cloud so far. As I mentioned, we are still in the progress of migrating to the cloud, but this particular arrangement here is quite mature now and is probably what I would say is at the forefront of what we have that's production ready. So you can see at the core of this is a Kafka cluster, and we're making heavy use of that as a mode of message interchange. So if you're not doing like a direct microservice communication, what can actually be a better model is to have Kafka messaging at the hub, and then you use publication and subscription members that are part of that communication pathway. And so with this model, it allows you to pump a lot of things into the Kafka system that can then get picked up by a QC analysis system, other processing workflows. It can be a means of getting data out to web services and to pipe to other services, such as an external solutions computing center. EarthScope actually has a couple of different universities that do specialized computing for GNSS data. So this is stuff that we've been building out in the cloud system, and we could have done this stuff on the on-prem systems, but the cloud has made it so much easier for us to get this started. So just touching on the theme of data ingress as relates to the cloud, there's basically no need to over-provision resources to handle the wide ingress pipe. So we don't have to pre-buy a whole bunch of computing systems. You can always spin up exactly what you need. We make heavy use of AWS managed services because there are robust analogs for the tools that we need. And what's nice is we don't actually have to administer those quite so closely. We make we make use of quick provisioning of multiple workers using Lambda functions, and we also use containers in many cases. We love the ubiquity and simplicity of S3 storage. It's really changed the way that we deal with data archiving and the access to data. Our archive can grow however big we need, and we can make use of smart hibernation logic for not recently accessed data. We love the ability to have multi-zone redundancy of systems. We really prize that redundancy. Workflow triggers are easy to do, and fan-out processing from FIFOs is lightweight and easy to set up. Much of that infrastructure is sustained by the cloud provider. These are just all the real bonuses. And I'm keeping my eye on the time, so I'm trying to speed up these last slides. So hopefully I don't go too fast.
You're good, Rob. Don't worry. I won't take up so much time at the end. So you take it.
Okay, I just don't want to run over time. Okay. Touching on the cloud concerns, naturally there are. And I know this is something that has gone through the minds of many people that have talked about going to the cloud is there are some things that are very concerning about making that leap. And I completely sympathize with those because I held those feelings myself. But important points that we touch on is you can import as much data as you want for free, but you pay monthly for what you continue to store. So it's not like we buy just some big huge RAID and suddenly it's kind of like it's basically paid for, except for maintenance costs. You have to consider licensing, but there's a definite bill to pay for the size of what we have in our archive. Egress costs, of course, are the big thing for a data repository. This is probably the biggest scary factor that we look at and that we're basically doing our cost estimates on. Pushing data out to the internet is expensive. And so we have to consider all of the processes that we do and the services that we offer, and consider how much we want to allow basically big, huge data to go out seamlessly to users. We want to enable seamless access as much as possible because these days machine learning is huge, and that this means big data access with the widest possible pipe. So we know the demand is out there. We want to find the smartest ways to make that possible. Databases can also be expensive to run. We've relied heavily on what have become fairly large databases in order to provide very quick access to indexable records. But this can get very expensive in the cloud, and so it forces us to start to think about perhaps more passive solutions of making that data available instead of using an active DB engine. There are many ways to solve a problem and many ways to architect, but some are just much more expensive than others. And so, with the dimensionality of how you try to do distributed access and distributed compute, there are ways to do it that are extremely expensive, and there's some ways that you find that are much less so. You can also run into enforced scalability limits imposed by the provider. So sometimes we have to go back to AWS and ask them to give us some consideration for allowing us to go over those limits. A provider-centric cloud architecture can lead to vendor lock-in, and we really have basically gone pretty much all in with AWS in terms of making use of the solutions they have. And that is really just because we made the final analysis that we would otherwise be overwhelmed with how much we have to administer and keep updated. And if AWS can just reliably take care of that, we see that actually as a cost saver. And just touching on egress costs again, I wanted to emphasize egress costs when I initially put this in, but what I really want to point out is it becomes an important factor that guides creative solutions for how we build our new data center. So, and we have some options such as negotiated limited waivers with our contract with the vendor, and also AWS, but other cloud solutions offer open data types of options where you can put a fairly huge amount of data into a place that's publicly accessible that you then are not having to pay for the egress costs. So these are the types of things that we grapple with. This image, of course, is familiar to those who are familiar with Grafana, and we've seen this represented in some of the earlier slides. So everybody in this meeting seems to be very cognizant of the importance of observability, and so we've had that be a major headliner in our new designs. And so we are conducting performance monitoring and latency tracking of all of our data ingress. We want to understand the health of our networks. What you can see is the NODA systems, and basically getting precise positioning streams. We want to know if there's any latency issues. We want to know if there's outages, and just kind of what our completeness is. So we're building out a considerable monitoring system that some fraction of that will be available to the public so that they can understand as well just how available our data is. We also have an important real-time mission in EarthScope. EarthScope is a key provider of low latency, real-time GNSS and GPS data for the USGS Shake Alert early earthquake warning system. So for everybody on the West Coast, you're probably familiar with Shake Alert because this has become an important potential lifesaver for the basically being able to do duck and cover in time for major quakes that occur. And the reason GPS data is particularly useful for Shake Alert is that the data it receives, because it's just measuring position on the ground, it doesn't saturate the way that seismic data will. Seismic data is very sensitive. It's like it has a microphone turned all the way up to 11 and can hear the slightest thing. So when a big earthquake happens, it causes those waveforms to peg. And so you can't, for really large quakes, you can't make good magnitude estimations. So GPS comes in and you can actually convert the position ground motion over time into velocity and acceleration figures. And then that can feed directly into the Shake Alert system for those most important, really big quakes. So that's a big part of what we've been building out in the cloud. Another concern is cybersecurity and sustainability, and we've really enjoyed working with our partners at Trusted CI that have helped us to try to improve our cybersecurity posture. So we have a unique opportunity as we build out the cloud to build a zero trust architecture. This means so many things in terms of having good authentication systems, as well as tightening down our security groups for anything you're deploying, excuse me, within the system. Limit how much things can talk across boundaries such as virtual private clouds and accounts. So that's one thing that we're taking seriously. Our workstations, our workstation clients go through VPNs, and any of our access to the cloud platform has really strong SSO login requirements. We're implementing a federated identity management system for all public access, and so we've been actually rolling it out for some time. We're not fully there in terms of blocking anonymous access, but that's the direction we're going. We want to establish good observability of systems, including alerting, which is what we're also folding in. FinOps, that's financial monitoring. So we're on constant watch for overspend. If we catch this early, we can rebuild a system that otherwise would be extremely expensive on our monthly bill. All running components and interconnects must be fully described and deployable as code. So this is known as infrastructure as code. And so that we've built out a pretty sophisticated and yet standardized system. We've built out some standards for our DevOps that allow us to build common components for deployment into the cloud system. And finally, all of the secrets that are used for authorization for access and being able to run and launch things in the cloud. All of that is stored in a key store internal to the system. So everything has to be referenced through, variables and key stores. And this is the final slide, I believe. So just to kind of give you an overall picture of kind of what our timeline has been so far, right at the bottom there, you can see we had the merger of Irisini and Navco on January 1st, 2023. So that's when we became EarthScope. By September 2023, we were able to close the Boulder facility, which had all their on-prem systems. And so the Gage facility moved fairly quickly into AWS. We still have a lot of work to make it a truly cloud native platform, but we managed to get ahead of the end of a building lease, basically, and get all the systems there. So that part of it is there in AWS. And we kind of go over to the right side of the picture. On the other wing, if you follow the analogy, the Sage facility is about 70% in AWS. The primary operations continue in the Seattle and Lawrence Livermore locations, but there's active communication between those locations and our cloud system. All the Sage Engage data are in AWS and are actively synchronized to multiple locations. And finally, we're not going on our projects rudderless. We have a good project management approach, and we actually now have a project management office that's overseeing all projects. So this will provide steering and direction to multiple cross-functional teams continuing to build out this system. And so finally, I'd just like to provide the acknowledgements for these fine individuals. Jim Riley worked very closely with me at the last minute to help me get these slides put together. And these other individuals here provided a lot of source material and checked my slides to make sure I wasn't totally off base. And all the talented developers I have to thank on the data flow team at EarthScope for having built out such an excellent system so far. So thank you.
Thank you very much, Rob.